In this video, we will discuss Albert Einstein's photoelectric effect. Physicist Albert Einstein was the first to describe the photoelectric effect fully, and received a Nobel Prize for his work. Understanding how this works revolutionized modern physics. Let's see photoelectric effect. The photoelectric effect is the process that involves the ejection, or release of electrons, from the surface of materials, generally a metal, when light falls on them. Equation for photoelectric effect is written as: generally, the material would be a metal, or conductor, which is a solid, that comprises several atoms. Atoms are composed with electrons, protons, and neutrons. Protons and neutrons are located at the center of the atom, and called as nucleus. Electrons, revolving around the nucleus, is shown in the following figure. In an atom, the electrons, that exist in the outermost orbit, are weakly bonded to the nucleus. When sufficient energy is supplied to the electrons, they will jump from valence band to conduction band. That is, they become free from the nucleus. Light can be used to push electrons, and eject them from the surface of a solid. That is, each particle of light, called a photon, collides with an electron, and uses some of its energy to eject the electron. This process is called the photoelectric effect, or photoelectric emission, or photoemission. Photoemission can occur from any material. But, it is most easily observable, from metals or other conductors. A material that can exhibit this phenomena is said to be photoemissive. And the ejected electrons are called photoelectrons. But there is nothing that would distinguish them from other electrons. In this experiment, we are going to understand the following terms: threshold frequency, work function, stopping potential. Threshold frequency, the minimum frequency at which photoelectrons emitted, is called threshold frequency. Below this frequency, whatever the intensity of light may be, no photoelectrons are emitted. This frequency is also called a critical frequency. This is different for different metals. Work function, the minimum energy, which is used to eject the electron from the atom, and away from the metal surface, is called the work function. This is denoted by W0. This is also different for different metals. Let's observe the photoelectric effect with an experiment. The photoelectric effect was first observed in 1887 by Heinrich Hertz. It was Philipp Lenard, an assistant of Heinrich Hertz, who performed the earliest, definitive studies of the photoelectric effect. Consider two metal surfaces that were first cleaned, and then held under a vacuum, so that they are not be affected by any surface contaminants or oxidation. The metal sample was housed in an evacuated glass tube, with a metal plate mounted at the opposite end. The tube was then positioned in a way that light would only shine on the metal sample, the one made out of photoemissive material. Such a tube is called a photocell, or an electric eye. Now, connect the photocell to a circuit with a variable power supply, microammeter, and voltmeter, as shown in the schematic diagram. Then illuminate the photoemissive surface with light of differing frequencies and intensities. Electrons, free from the photoemissive plate, would give it a slight positive charge. Since the second plate was connected to the first by the wiring of the circuit, it too would become positive, which would then attract the photoelectrons floating freely through the vacuum. The photoelectric current generated by this means was quite small, but could be measured with the microammeter. It also serves as a measure of the rate at which photoelectrons are leaving the surface of the metal photoemissive material. But the power supply is wired into the circuit, with its negative end connected to the plate that is not illuminated. If we apply voltage to the metal surfaces by varying the power supply, this sets up a potential difference that tries to push the photoelectrons back into the photoemissive surface. When the power supply is set to a low voltage, It blocks the least energetic electrons, reducing the current through the microammeter. Increasing the voltage drives more energetic electrons back, until, finally none of them, are able to leave the metal surface, and the microammeter reads 0. The potential at which this occurs is called the stopping potential. Stopping potential, the potential difference that stops the electron from cathode reaching the anode and reduces the current to 0 in the circuit, is called stopping potential. It is a measure of the maximum kinetic energy of the electrons, emitted as a result of the photoelectric effect. It is essential to know the kinetic energy of the photoelectrons. The expression for stopping potential is given by. What Leonard found was that the intensity of the incident light had no effect on the maximum kinetic energy of the photoelectrons. That is, when the metal sample was exposed to a very bright light, those electrons which got ejected had the same energy as those ejected from exposure to a very dim light of the same frequency. However, more electrons were ejected by a bright source than a dim source, as per the law of conservation of energy. Later, the American physicist Robert Millikan, in 1914, found that light with frequencies below a certain cutoff value would not eject photoelectrons from the metal surface, even though the light source was bright. The cutoff value is called threshold frequency. Experiments showed that increasing the light frequency increased the kinetic energy of the photoelectrons, and increasing the light intensity increased the current. Hence, the number of electrons emitted, and their kinetic energy, depends upon the potential difference between the two electrodes, the intensity of incident radiation, the frequency of incident radiation, the photometal used. In this video, we have discussed photoelectric effect.